Have you ever been on a flight, looked out the window at the clouds whizzing by, and wondered, how fast are we actually going? Well, the answer is way more interesting than you'd think. Let's dive in.
You know, when a pilot glances at their airspeed indicator, it's not at all like you looking at the speedometer in your car. That little dial in the cockpit is answering a totally different and much more important question about flying.
And here's the big secret right up front. That instrument, it isn't really measuring speed at all. No, it's measuring pressure. And once you wrap your head around that one little idea, everything else about airspeed just clicks into place.
So, to understand why pressure is the name of the game, we first have to talk about this invisible force that's constantly acting on a plane in the sky.
It's called dynamic pressure. See, it's easy to forget, but air actually has mass. It has substance. So as a plane carves its way through the sky, the air pushes back. And that push, that kinetic energy from all those air molecules hitting the plane, that's dynamic pressure. It's the force the aircraft actually feels.
And this is the little bit of math that makes it all work. Q is our dynamic pressure. It's equal to 1/2 times rho, which is just the symbol for air density, times v for velocity or speed squared. And trust me, that little squared part is a really, really big deal.
So what does that look like in the real world? Okay, imagine a plane flying at 100 knots, down near sea level. The air is pushing back with about 16.6 hectopascals of pressure. It's a small force, but it's definitely there.
But what happens if we double our speed to 200 knots? Now you might think the pressure just doubles, right? Wrong. Remember, the speed is squared in that formula. So doubling the speed doesn't double the pressure. It quadruples it, making it jump all the way to over 66 hectopascals. This relationship is everything in aerodynamics.
All right, so dynamic pressure is obviously super important, but how does a plane actually measure it? Well, it uses this brilliantly simple little piece of engineering.
And the idea actually goes all the way back to the 18th century, to a French engineer named Henri Pitou. He knew that to truly understand flight, you first had to figure out how to measure these invisible forces. So he went and invented a device to do just that. And the way his system works is just genius. Step 1. A little tube facing straight into the wind, that's the pitot tube, captures all the pressure. That's the dynamic pressure for moving, plus the normal ambient air pressure, which we call static pressure. Step 2, some little vents on the side of the plane measure only that static pressure. And then step 3, the clever part. The instruments just subtract the static pressure from the total pressure. And what are you left with? Just the dynamic pressure. Brilliant.
And that simple little subtraction problem reveals the core truth here. The airspeed indicator is really just a pressure gauge in disguise. But because it's measuring pressure instead of actual speed, a pilot has to think about airspeed in 4 totally different ways.
The first one is indicated airspeed, or IAS. This is literally what the pilot sees on the dial. It's that raw, uncorrected pressure measurement, just translated into knots. But it's just the starting point.
You see, that raw reading can have some tiny errors. Depending on where the sensors are placed, or if the flaps and landing gear are down, the airflow can get a little messy. So we apply a correction for that, and that gives us calibrated airspeed, or CAS. It's just a slightly cleaned up version of what the instrument is sensing.
But then, as a plane gets going really fast, we're talking above 300 knots or so, the air itself starts to act weird. It actually starts to compress, or kind of pile up inside that pitot tube, which gives you a pressure reading that's artificially high. So we have to correct for this compressibility effect, and that gives us our third speed, equivalent airspeed, or EAS.
A good way to think about it is like this. At low speeds, air flows past the plane smoothly, kind of like water. But at really high speeds, you're hitting the air so hard that it can't get out of the way fast enough, and it basically gets squeezed. EAS is the speed that accounts for that squeezing effect.
And that brings us to the one you've been waiting for, true airspeed, or TAS. This is the big one. It takes our equivalent airspeed and corrects it for the single biggest factor of all, the density of the air. This is the plane's actual, honest-to-goodness speed through the chunk of air it's flying in.
And the difference this makes is just massive. I mean, think about it. At 40,000 feet, the air is about 4 times thinner than it is at sea level. So to generate that same amount of dynamic pressure, that same push that the wings need to create lift, the plane has to fly twice as fast through that thin air. So a pilot's indicator might say 250 knots, but their true speed through the sky is actually 500 knots. So here's a quick cheat sheet to pull it all together.
You start with the raw, indicated pressure reading, then you correct it for position errors to get calibrated, then you correct that for air compressibility to get equivalent, and finally, you correct that for air density to find your true airspeed. It's just a ladder of corrections to get from what the plane feels to how fast it's actually moving.
But when you get up to really high altitudes and really high speeds, even true airspeed isn't the whole story. You need a completely different frame of reference, the speed of sound itself.
And that's where the Mach number comes in. It's actually pretty simple. It's just a ratio of your true airspeed to whatever the speed of sound is right there, which changes with the temperature. So if you're flying at Mach 0.8, it just means you're going at 80% of the speed of sound in that exact spot.
And why does this matter so much? Well, as a plane gets close to the speed of sound, the air flowing over the curved top of the wing has to speed up. And it can actually go supersonic even when the rest of the plane is still subsonic. That creates shock waves that can mess with your lift and control. So knowing your Mach number is absolutely critical to staying out of that danger zone.
Okay, so we've got all these different speeds floating around. Indicated, calibrated, true, Mach number. Which one does a pilot actually use to fly the plane? And this is where it all comes full circle, right back to the beginning. All of the most critical speeds for safety, your takeoff speed, your landing speed, and especially your stall speed, they're all based on dynamic pressure. They're all given as indicated airspeeds. See, the wings don't care how fast you're going over the ground. They only care about one thing, how much air pressure is flowing over them to make lift. And that's the force that keeps the plane in the sky. So the next time you're on a plane, just remember this. The person up front isn't just a driver pointing the plane where it needs to go. They are constantly managing an invisible force, balancing this delicate, beautiful equation of pressure, density, and speed. A pilot isn't just a master of flight. They are a master of pressure.